Hello everyone. So this time I'll be solving a few problems regarding chemistry of metals. And I think I have four examples in this video. And hopefully this would guide you in solving additional problems when it comes to chemistry of metals. In our lecture class, we already discussed the different properties, characteristics of metals. Also, we've already identified where they are at the periodic table. And there were also a few examples given during our lecture class. So these are just additional problems that you might want to go over so as to help you in solving word problems when it comes to chemistry of metals. So my first problem here is, it says, let's just zoom that a little, write a balance equation to represent the reduction of iron 3 oxide or ferric oxide by carbon monoxide, then compute for delta G, or the Gibbs free energy, at 350 degrees Celsius for this reaction. Okay, we are given a table for our enthalpies, or heat of reaction, as well as delta S, which is entropy. Okay, let's just take note of that. Probably can write it here. This will be our entropy, and this will be our heats, or heat of reaction. And we have a formula later on that we'll be applying. For this problem, we're looking for delta G, which is Gibbs free energy. Okay, I think we have all what we need to be able to solve the problem. So let's start by, I guess, getting the balance equation. So for the easiest way to identify the equation, maybe we can read it out loud, or you can just analyze it. It says ferric oxide. So, and if you are already, you're actually familiar with it already because in lecture we already took it. So ferric oxide is actually, let's just change pen color here. That will be better. Okay. Ferric oxide, or iron 3 oxide. Okay, let's, and then it says by carbon monoxide. So we have to make it react with carbon monoxide. And then, of course, when this happens, when this reaction happens, we can draw out our raw iron. So we can just say that's Fe. And of course, the byproduct in such reaction, since when a metal or a compound is mixed with carbon monoxide, we can assume at the product side there would be carbon dioxide. And then we just check if it's balanced. If it's not balanced, we'll balance it. So how many irons do we see? We have two on this end. We only have one here, so let's put two here. So that balances iron. And then we can check for oxygen and carbon. Carbon, we have one. Okay, maybe we can put carbon as the last one for balancing. Maybe we can take oxygen. So we have oxygen 1, 2, 3, 4, and we only have two here. So what can we do? Probably we can try putting 3 here, and that would make it, and probably another 3 here. Let's check if that's gonna be equal. Yeah, that's gonna be equal. So that will be 3 times 2, that's 6 oxygen. 1, 2, 3. 3 times 1, that's 3, that's 6. And then carbon 3. So this is balanced. So if you will be asked of the balance equation, then this is the balance equation. Or maybe you can write that. So this is our balance equation. And from here, we can already solve. We know that the formula for delta G is actually the Gibbs free energy is equal to the heat minus the temperature times delta S. Okay, so what do we need? We actually have T from the problem. We can see that our T here is 350 degrees Celsius. Maybe we can note it here so that it will be readily available later. So what can we do now? Let's first take parts of the equation. We can get delta H. Oops, okay. Delta H now, when you see a delta, it's always the delta H of our products minus the delta H of our reactants. And we know that this would be our product side and this will be our reactant side. Okay? By now, I believe and I'm really confident that at this point you won't be confusing the product and the reactant side. Okay, so what do? We just simply get the values from our given table. Okay, let me just make that smaller so that we can have more space. So for the product, we have iron and carbon dioxide. So we check on carbon. Okay, we have it here. I'm sorry. We're checking on iron. Iron is here. So 0 and 0.02, whatever. Okay, let's do that here. That's 2 times 0. That's 2 times Fe is 0 here. We can check it here, here. And then plus, of course, we have to add. That'll be 3 and something for carbon dioxide. That would be negative 393.5. Okay, let's check that. Carbon dioxide, there you go. It's 393.5. Okay, and then we get the values of H for the reactant. So for the reactant, we just simply get for ferric oxide, we check it here, ferric oxide, there you go. It's negative 824.2. So let's just move that a little. Negative 824.2 plus we have 3 moles of carbon monoxide, and that will be negative 110.5. Okay, and then of course, let's do our magic. Let's compute that. Using our calculators, we're getting negative 24.8 kJ per mole. Okay, where did I get that unit? Kg per mole or kilojoules per mole. It's of course from this. It's here. So I can say that my total here is in kJ or kilojoules per mole. Now we can proceed in getting delta S because we cannot still compute our Gibbs free energy because we don't have our entropy. Okay, so let's compute that. Our delta S now. We do the same thing but now using entropy values. So that's also the delta S of the products minus the delta S of the reactants. Okay, there you go. And then we just get the values from the table again. So that's 2, and then that's 0.273 from the table, plus 3, 0.2136. We can check that. It's here. That's 0.0273 and 0.2136. Okay. Just be careful in getting the values from the table because one wrong value will make your solution incorrect. So that will be, there's my minus signs there, 0.0874 plus 3 times 1976. Okay. And if we're getting delta S now, again, using our calculators, what I got is 0.0152 kJ per mole. It's consistent. Okay, maybe we can identify our answers so that later on it'll be easier to get them. There you go. Now we can already solve for delta G. I'll probably just include it here. It might fit. Yeah, it will fit. So our delta G, our Gibbs free energy, is delta H minus T delta S. However, take note that T should be in Kelvin. And what we're given is in Celsius. So we can just substitute straight out 24.8, that's kg per mole, remember that. And then minus 350, the given, plus 273.15 multiplied to 0.0152. And delta G now, our final answer is negative approximately 34.27, and of course that's consistent mole. Okay, so that will be our answer for this one. Okay, by the way, this is kj mole, because you might be wondering, I forgot to put Kelvin. There I go. So as to be able to cancel out Kelvin here, so that's kj per mole. So this will be our first problem. Hopefully, you can now solve on your own a problem when it comes to Gibbs free energy. So just a wrap up for this problem, we were asked to get the balance equation of the reaction, and then of course we have to know the formula for Gibbs free energy, and then we get the parts or the unknowns. We started with getting delta H, and then we proceed to getting delta S, and then of course just substitute the given T, and we're getting delta G as negative 34.27 kg per mole. Quite long, but very simple. Okay, now maybe we can proceed to another one. So we have another problem. Let's just read the problem. It says to inflate a life raft with hydrogen to a volume of 25 liters at 25 degrees Celsius and 1.10 atm or atmosphere, what mass of calcium hydride must react with water? And there's a hint given to be able to help us solve the problem. Write the first balance equation for the reaction. Okay, let's just try it. Okay, let's just first get the given. Maybe we can write the reaction. So it's the reaction of calcium hydride and water. So let's just create an equation. So calcium hydride is CaH2, and you're making it react with water. But I believe in the lecture, in our canvas, we have the reactions given there. So the end product or the product will be calcium hydroxide and a byproduct of hydrogen gas. Let's balance that. Okay. You can refer to your notes on the combinations of metals with water, the hydrides part of our lecture. So this part is purely for problem solving. So if you need a refresher on the combinations, you can always go back to our notes on the lecture part. Okay, when a metal is combined with water, when a metal is combined with hydrogen gas, etc. Okay, so we also have to get the different values from the problem. We have a given volume. The volume is 25 liters. We also have a given temperature. Temperature is 25 degrees Celsius. We also have, we can already change this to 298.15 Kelvin. Remember, we're working with standard units. And we also have pressure. Our pressure is 1.1 atm or atmosphere, and R is a constant, and R is 0.0 0.821 liters per atm mole Kelvin. Okay, so let's continue. So this is an ideal gas law problem. So what do? We just get PV equals nRT. Okay, so that's an ideal gas problem or ideal gas formula. So let's substitute the values that we have. Okay, or what are we looking for? Let me see. We're looking for the mass of calcium, but in the formula, we don't have mass, but instead, the formula gives the value of moles. But we can always, of course, get a value of moles first, and then later on, we'll be able to derive the mass. Okay, so let's just, we have everything. We have pressure, we have volume, we have R, we have T. So we can actually isolate N. N is equal to PV all over RT. And let's just substitute our values. So that's 1.1 multiplied to 25 liters. I won't put the units anymore. Maybe later on your own, you can just insert the units just because the space is too little. So this is 821 and I have 298.15. Okay. And I'm getting N here as 1.123 moles of hydrogen gas. So what's next? We can use the mole ratio. Okay, we check the original balance equation and we can see that here our N is 1.123 moles of hydrogen gas. So how many moles of CaH2? We have 2 moles of CH2. Okay, actually we have 2 moles of hydrogen gas on the original problem. So let me just add a sheet. Maybe we can add a sheet. Where is that? Because I need an extra sheet for this. Okay, with that one. Okay, let's just continue. Now let's get mole ratios. For for mole ratios, we have moles of CaH2. This will be equal to what we computed, moles of hydrogen gas all over 2. 2 is coming from the original. So this is now equal to 0.56 moles of CaH2. So now I believe we can get the mass. Mass now, how do we get it? Not a mass, that's mass. Of course, we get the molar mass of CaH2. This is 2 times 1.01. And then, of course, calcium is 40.08. So the total is 42.10 grams per mole. And of course, we can already compute for mass. This will be equal to molar mass times the number of moles. And molar mass is 42.10 times 0.56. And finally, we can already get what we're looking for initially in the problem. This has 23.58 grams of calcium hydride. Okay, so that's our final answer. So let's recap what we did. So we were given a problem. It's the reaction of calcium hydride with water. So we first, of course, we always start with the balance equation and then we get what is given. So fortunately, in this problem, we were given volume, temperature, and then P and R were also given. So we just get the ideal gas law formula so that we get PV is equal to nRT, and then isolating N, we get N, we get the ratio from the original equation, get the mass of calcium hydride, and finally get the molar mass of calcium hydride, and finally get the mass from all those data. Okay, so the answer here is 23.58, or approximately 23.6 grams. Okay, so what's next? We have two more problems, but these are way shorter. I believe the solutions are shorter than the first two. So, what if you're given a simple one like this? Given the following reaction in which two ethylene molecules combine with hydrogen to form butane, you can use the table for thermodynamic data at 298.05 Kelvin to calculate the delta S for this reaction. So we're given the reaction right away. So no need to balance or no need to think it over. What will be the reaction? So let's just rewrite that. That will be 2C2H4 plus hydrogen gas yields, of course, this is butane. Butane is C4H10. For us who love SAMG, we're very familiar with butane. Okay, now we're looking for delta S, and we know that delta S is simply delta S of our products minus the delta S of our reactants. So from our thermodynamic data table, I did look for it. Just hopefully my values are correct. So for entropies, C2H4 and then H2 and then butane, this is 219.3, 130.7, and 310.2. These are all in joule per mole Kelvin. Okay, and we can just go straight in getting the enthalpies. So delta S now, the enthalpy, the entropies. So that's 310.2 minus 2 times 219.3 plus H2 is 130.7, and delta S now is equal to negative 259.6 joule per mole Kelvin. So perfect. We have our answer. So in this problem, we really didn't get a lot or didn't really derive a lot of data because we can just get the values from our thermodynamic data table. I believe you have that, okay? And for the last problem, we have, again, we're looking, it's still going around the Gibbs free energy equation. So let's read the problem. The heat of fusion of crystalline polyethylene is approximately 7.7 kg per mole, and the corresponding entropy change for melting is 19 joules per mole Kelvin. Use this data to estimate the melting point of polyethylene. And what we need to do here is set delta G to 0. Okay, so we're just asked for the temperature. Okay, of course we know that our formula is always delta H minus T delta S. So let's isolate our T. T is, of course, delta G minus delta H all over delta S. Okay? Yes. Okay. And then all we have to do is substitute. We have 0. It's given in the problem because you might ask me, Mom, why is it 0? It's because we are being asked to set delta G to 0, and then we put 7.7 here, joules per mole. Oh no, that's kg per mole, right? That's kg per mole. Okay, and then we have 19 joules per mole Kelvin. And what I'm getting here is T is equal to 405.26 Kelvin. Okay, so if you look at all four problems, they just use a single equation gives free energy, but what we did was actually look for different values in that equation. We started with, for the first problem, we were looking for delta G. For the second problem, it's an ideal gas law problem, so it's not related to that. For the third problem, we were able to get delta S in the equation of the Gibbs free energy. And for the fourth one, we were asked to get T. So what's important to note is that when you're given problems like this, make sure that you isolate the given or extract the given from the problem so that you'll be able to manage and get the correct values from the tables and all. Okay, so hopefully these four problems would help you in your review or when you're studying chemistry of metals uh, solved problems. Okay, okay, and of course, till the next video. Thank you so much, and just practice solving.